Thank you very much. Our last speaker in this session is going to be Professor John Mack, who is going to present on rational design of Porphyin and BODIPY analogs for biomedical applications, further progress and future perspectives. The podium is yours, Professor.
Okay, so basically, when I signed up for this conference, it was going to be a computational chemistry session. So I'm feeling a little bit out of place with albatrosses being discussed and stuff, but never mind. Very interesting talk I have to say about the albatrosses. So the background to what I have been doing is using Gaussian to rationally guide the synthesis of porphyrin and BODIPY dyes towards specific applications. And the big advantage of CHPC from this standpoint, yes, it's commercially available software, and yes, you can do it to a certain extent on a desktop, but by the time you get to the size of some of the dye molecules I'll be talking about, if you want to do a TD-DFT calculation, you need a large memory allocation. And one of the biggest advantages of CHPC from my standpoint is that using up to 45 gigabytes as a memory allocation is straightforward, and that can facilitate calculations that would simply not be possible on a desktop alone using this commercially available software. So the background is I'm going to be talking a lot about porphyrins, 16-atom, 18-pi electron system on the inner perimeter of the ligand, and I'll be talking a lot about applying a conceptual framework that was developed in the 1970s to deal with semi-empirical calculations, but is still useful in the present day with TD-DFT. We've got two sets of frontier orbitals. The highest occupied have 4 nodal planes, angular nodal planes, the lowest unoccupied of 5 nodal planes, and I'll be using a nomenclature that's shown here. A means that there's a nodal plane aligned with the symmetry-defined y-axis, and S means that there's significant MO coefficients on the y-axis. These are the HOMO level, these are the LUMO level. So basically, thanks to CHPC and calculations I was able to do in quite large porphyrin molecules, I was able to get a publication in Chemical Reviews looking at trends in these 4 orbitals that I've just described, and describing how we can understand how changes to the structure can modify both the electronic structure and the optical spectroscopy of porphyrin-related analogues. And moving on from that, basically, let's do something useful. Let's use molecular modeling to see if we can identify target molecules for synthesis that will give us the best properties for specific applications. First one here, photodynamic therapy. We have a porphyrin dye acting as a photosensitizer. If it accumulates selectively in cancer tumor cells, and if we shine light, we can form reactive oxygen species and use that to destroy the cancer tumor, is the guiding principle here. And this has been there's been dyes on the market for this since the mid-1970s. The first one was photofrin. It's an oligomer of porphyrin. And the big disadvantage is that if we're going to carry out photodynamic therapy in human tissue, the human body tends to be transparent to human tissue, tends to be reasonably transparent to light in the 620 to 850 nanometer region, and porphyrin, the most common synthetic porphyrin, has very weak absorbance in this wavelength region. So our goal is to shift the spectral band towards the near infrared region and to intensify it if we can. That means lower drug concentrations will ultimately be needed. And the most important aspect is that we're between endogenous chromophores, like hemoglobin, and where water will absorb as well. We've got a transparency window where we can generate this singlet oxygen with our photosensitizer dye. So there's different approaches we can use to modify the porphyrin ligand, and what we've looked at is reducing a peripheral bond, introducing a direct peripheral bond, and flipping one of the nitrogen atoms to the outer periphery of the ring. And our starting point for this, in collaboration with Dr. Edith Amuhaya in Nairobi in Kenya, was to replace phenyl rings that are typically used in synthetic porphyrin molecules with thiophene rings. And I'm not going to belabor all the details here, but essentially we get a smaller homo-lumo gap. And the big advantage of thiophene is that because it's five-membered, it can rotate more easily into the plane of the porphyrin ring. There's less scope for steric hindrance. And at that point, you get a stronger mesomeric interaction with the porphyrin pi system. And through the effect that has in the frontier molecular orbitals, you can redshift the spectral band further into the phototherapeutic window. So we get to be on the edge of the phototherapeutic window. We've been focusing a lot on tin complexes. Transaxial ligation means that we can eliminate aggregation effects, and that helps to maintain the photophysical and photochemical properties of the ring and of the ligand, and making it suitable for this specific application. I'm using a lot of time so far. I need to speed this along. So that was one thing we can do. We can modify the meso arrow rings. The other thing we've looked at is to add bromine atoms to the ligand periphery. And now we can get a shift of the spectral band and intensification out to about 670 nanometers, so deeper into the phototherapeutic window where we want to be. When we did theoretical calculations, it became clear that what's happening is that once you add the bromines here, there's a saddling of the ligand to accommodate the bromines and the meso arrow rings here. And the effect that this has on the frontier orbitals is a destabilization to a significant extent of the highest occupied molecular orbital. And this narrows the homo-lumo gap, and we get a redshift and also an intensification of the spectral band, which is what we want for the photosensitizer properties. In a similar sort of way, when we looked at chirals, here we have a direct pearl-pearl bond, and because of the effect of the introduction of that bond, when we look at what's happening with the frontier orbitals, we get a narrowing of the homo-lumo gap, and again, that's helping to shift deeper into the spectroscopic window where we want to be to enhance the photosensitizer properties. But we're talking about a fairly small redshift of the spectral band at that point. What works a little better is if we reduce the peripheral bond. This is the same approach that's used by chlorophyll in nature. And Again, we can use molecular modeling to figure out what's happening with our frontier orbitals and why we're getting a red shift of the spectral band. Essentially, two of the molecular orbitals are destabilized to a significant extent by introducing the reduced bond on the ligand periphery. End confusion is perhaps the most exciting one because we can move the band out to almost 800 nanometers, which is deep into the window where we need to be and well away from all endogenous chromophores. And again, we can use our molecular modeling, TDDFT, CHPC resources to rationally figure out what's happening with the homolumal gap and figure out what further changes we could make to the structure to possibly further enhance it. So by carrying out molecular modeling, we were able to decide that extending the pi system with a thiobarbituric acid group like so might be an interesting change to make. And that enabled us, we started off about 600 nanometers, now we're past 800 nanometers by flipping an nitrogen atom to the outer portion of this parole and extending the pi system with a thiobarbituric acid. So now we're very deep into the phototherapeutic window, and also we have more intensity with this band, which is good from the standpoint of the application. And again, it's all about using the calculations to rationally guide us towards the dyes that will give us the properties that we want. And where is this heading now? I was talking initially about adding thiophene rings. One of the advantages there is that that allows us to conjugate to nanoparticles, gold nanoparticles, for example, which can help to selectively deliver the photosensitizer dyes to the cancer tumor cells and avoid the healthy cells. And again, by using molecular modeling, we were able to determine that if we start with phenyl and we add hydroxy and methoxy groups here to have a vanillin ring, that actually results in a significant redshift and intensification of the spectral band that we're using to photoexcite the dye and to generate the oxygen radical and singlet oxygen species that we're using to eradicate the cancer cells. And this is an approach that we will move forward to other types of analog as well, so that we can have a dye that's potentially aqueous soluble and it's further redshifted and intensified. So again, molecular modeling helps us to select the dyes that are likely to give us the most suitable properties. So we're not doing it with serendipity, we're doing it with a rational approach. And where things are headed, many of the photosensitive dyes that we've been using, we're also going to use them as part of a photoelectrochemical detection method for cancer biomarkers. And again, we'll think about using molecular modeling to determine what can give us the optimal outcome in that context. It's not just cancer cells that we can eradicate with the photodynamic therapy approach. It can also be used for bacteria which have developed antibiotic resistance. It's a growing crisis in modern medicine that antibiotics are no longer working on bacteria like Staphylococcus aureus, for example, hospital superbugs. And one of the possible alternatives is the photodynamic therapy approach, because the bacteria are unlikely to develop a resistance to singlet oxygen and other reactive oxygen species. Where does CHP-PC come into this? I'm maybe drifting a little too far from that angle in this talk. Another thing that we can look at here, we're looking at Badipi dyes. It's kind of half a porphyrin, if you like. We're adding heavy bromine or iodine atoms to the Badipi dye so that we can have intersystem crossing. We can generate singlet oxygen to eradicate the bacteria, hopefully, with the photodynamic therapy approach. And what we've been looking at here with molecular electrostatic potential maps is, and also calculated dipole moments, we're trying to find a rationale for why certain of these dyes are working better than other of the dyes and being taken up by the bacteria, and subsequently having the bacteria eradicated when we shine light and we generate the reactive oxygen species. So finally, I think I was going to talk about optical limiting. I've got maybe 3 minutes left, I believe. Yep, I'm keeping an eye here as well. So what's optical limiting all about? This is maybe getting a little dated now, but this is from, there was a military coup in Egypt about 10 years ago to overthrow Mohammed Morsi. And what we have here is all the pro-secular Egyptian people. And what they're doing is they're celebrating the coup by shining laser pointers at a helicopter. And that's a spectacularly silly thing to do, because it's going to blind the pilot who's flying above these demonstrators. So about 10 years ago, AMSCOR approached us at Rhodes University, Institute for Nanotechnology Innovation, looking for ways that we could have molecular dyes that could be coated onto the cockpit window so that intense laser light or laser pointer light could be attenuated by the coating with the molecular dye on the cockpit window. And essentially, we use an approach called Z-scan. We've got our molecular dye in a sample cuvette here. We're moving it through the lens focus of a laser beam. And by doing this, we can determine whether the molecular dye has nonlinear optical properties with respect to transmission of the light. And essentially, if you have an excited state which can absorb the light to a greater extent of what's happening in the ground state, you can have higher absorption of the instant laser light at high light intensities than you would normally have at ambient light conditions. And that means that you can potentially protect the eyesight of the pilot from the effect of the laser pointers. How does this get back to CHPC again? We can try and determine which dyes are going to give us minimal absorbance across the visible region under ambient light conditions. That's one thing. We can look at how we can modify the structure of the dye to do that. And we've also, again, we're looking at molecular electrostatic potential maps, dipole moments, to see if we can determine if there's any correlation between dipole moment and the parameters that we generate from Z-scan for the non-linear optical properties. 5 seconds to go by the looks of things. So, I'd like to emphasize again that yes, it's commercially available software, but the large memory allocations available from CHPC really help us a lot. Wouldn't be possible to do many of the things we're doing without access to CHPC. And just some acknowledgements, and thank you, my funders. And I'll finish up there. Thank you for your attention.